If you take a drop of blood and sandwich it between this microscope slide and this slipcover, and shine a laser beam through the blood, a pattern emerges on the other side, and if you measure that pattern, you can determine the diameter of your red blood cells. To do that uses this concept of diffraction and interference, and that's our topic for today. Before we learn how waves spread out and fill in behind barriers, let's just remind ourselves of particles. So all these like sand particles hitting this barrier here, they're blocked, and this is a shadow, and those particles do not fill in behind. But waves do. If these are waves coming in and these posts are the barriers, the wave fills in behind and it just curves around that barrier. To understand why that does, let's imagine ourselves dipping our finger into the pond repeatedly, creating a series of crests and troughs, and those waves propagate outward. I'm going to draw it like this, just dipping my finger in the same place, making these concentric circles. We'll say that the orange circles are crests and the blue ones are troughs, but dip your finger in there, that's what it's going to look like. Instead of dipping one finger in, let's dip 3 fingers in. Each finger is going to be a source of its own concentric circles or waves. And those waves are going to interfere with each other. So like right here, we have 3 different crests all on top of each other. That's going to create a large crest. And here we have 3 troughs all lining on top of each other. That's going to make a big trough. If crests fall onto troughs, you get destructive interference and you don't get any net movement of the water. Instead of dipping my finger in 3 times, let's dip them in 7 times, and this pattern emerges, and it gets to be kind of complex. You can see that in front of it, all these crests and troughs kind of line up, and you see a pattern here, but off to the side, not much pattern develops. So if we had a series of wave fronts, parallel wave fronts, so crests and troughs, what Huygens Principle says is that on a wave front are an infinite number of points, and every point behaves as its own source of waves. So when these waves spread out, there's an infinite number of them, there's lots going on, but a pattern emerges, and we can see that it's just as if the waves were propagating out like that. Again, Huygens Principle is so important, but it helps us to understand why waves bend around barriers, which is called diffraction. So if this is a barrier and I had these parallel wave fronts and hitting that barrier, it would be very difficult to understand if we didn't know Huygens Principle. So let's say that this wave front had all sorts of points, their own source of waves, and same thing down here. So from those points, we're going to get a series of concentric circles. Now it looks complex, but just in the middle here, there's no real net pattern that develops. You have crests and troughs, and they're kind of overlapping everywhere, but no net pattern develops. On the sides here, you can see that there's a lot of crests and troughs overlapping here. And even if you look off into this area here, the orange crests and troughs are closer together and they don't completely cancel out. I should say the orange crests are closer together and don't really cancel out with the blue troughs because they're a little bit more spread out. And you can see that the waves started to bend around that barrier and will meet out there somewhere. And instead of having just a single barrier here and open on the sides, let's have it open in the middle and the barrier on the sides. We'll call this a slit, a tiny little opening. But again, we have Huygens Principle. All these points behave as their own source of waves, and these waves propagate outward like this, and there's going to be this overall area in the middle here where all these crests and troughs, crests here, troughs there, lining up. But even if we look off to the side there, all those orange lines, all those crests are kind of close together. The blue troughs are spread out further, and there's a net pattern that develops, an overall crest that develops here, and an overall trough that kind of develops there. And it's spread out at some angle. Let's see what might affect how much it spreads out. If the opening was smaller, and I did the exact same thing with the same number of dots and the same number of waves, this is what's going to happen now. It's the same thing, but just the waves that were out here got blocked. And if we look closely at the pattern here, all in through here are crests, and all in through here are troughs, but they extend a little further this time. That they in through here they canceled out, but right in through here is all troughs and all crests, and it's spread out at a little bit larger angle. If it was even smaller, and we did the same thing, blocking the ones that were out here, and do the same thing here, we can see that the crests here extend past that and even all the way over here before they start to overlap. So this is going to diffract or spread out a lot. And if the opening, that little slit, is really small, so there's just a couple of points there creating their own source of waves, there never really was a chance for the troughs to overlap with the crests because these weren't far enough apart to do that, and you get complete diffraction. It spread out beautifully all the way around like this. So the smaller the opening, the more it's going to diffract. And if that opening is really small, it's going to diffract a lot. Now this idea of big and small are relative terms. So what is it relative to? Well, if the size of the opening is large in comparison to the wavelengths that are being shown at it, it's not going to develop much pattern off to the side here, and it's only going to spread out or diffract a little. I'm going to keep that opening the same size, but send larger wavelengths at it. Well, relatively speaking, this just got smaller compared to those waves, and you can see that it diffracts out there more. And if I kept the opening the same and send even larger waves at it, they're going to diffract all the way around here because there was no troughs falling into that area there. So an example of this is if you're standing in the corridor here and you move off to the side, you can't see him anymore. In fact, he can't see you anymore. I know that's mind-blowing, but he can still hear you. So let me explain. So here's the size of that corridor, and sound waves are really kind of large wavelengths in comparison to that opening. So they're going to diffract around a lot. Light waves are super small in comparison to that opening, so they're not going to diffract. They're not going to bend around very much. So far all we've done is explain that if the wavelengths are large and the opening is small by comparison, the waves are going to spread out a lot. That's diffraction. And Huygens' principle, treating every point as its own source, explains why that happens. But now we want to take that a step further. We're done with diffraction. We know that waves are going to spread out if that opening is small. But now we're going to revisit interference. If there's two openings, so these waves here are spreading out because that opening is small. These waves are spreading out because that opening is small. But the waves coming out of here are going to interfere with the waves coming out of there. And there's places where it's going to be really intense, really big crests, really small, or really big troughs. And if we focus in on this spot here, we can see it's real dark and light, dark and light. If this is sound, it would be a really loud sound. If it was light, it would be a very bright light. If it was water waves, they'd be really tall waves. Okay, but right in through here, really intense. Off to the side there, at a little bit of an angle, it's not really intense. In fact, you wouldn't hear any sound or you wouldn't see any light right there. But again, back over here, we see that same pattern we saw over here, and the pattern repeats. No sound or light there, but very intense sound at some angle over there. So let's see if we can understand why that happens. the distance from this opening to here and the distance from this opening to there were the same. Okay, but if they're off to the side here, the distance from here to here is going to be longer than the distance from here to here. In this example, it was 1, 2, 3, 4 wavelengths from here to here, and only 3 wavelengths. There was a difference in the length of the path that was a multiple of the wavelength. In this case, it was just 1 wavelength. So L would be the difference in the length of the path, and if the difference in the length of the path is a multiple of the wavelength, then the wave that came from here is going to align exactly 1 full wavelength behind, but 1 full wavelength behind is aligned. It's in phase, and that would be a very bright spot. Now, previously I've been using orange and blue to represent crests and troughs. I'm moving away from that now. All these circles are crests. The purple ones are the crests coming out of this slit, and the blue ones would be the crests coming out of that slit. And this is the straight distance from those slits to our screen. From here to here and from there to there, there was no difference in the length of the 2 paths. So in this case, m is equal to 0. There was no difference in the wavelengths. But off to the side here, see how all these crests are overlapping, and all the troughs would be overlapping as well. This path was 1 full wavelength greater than that path. So this is just 1 full wavelength. So the difference in the path was 1 wavelength. M was equal to 1. Off to the side, it's going to be different by 2 wavelengths. So M equals 2. Even over here, this path would be 3 full wavelengths greater than that one. And again, they line up crest on crest. And off at some great angle off to the side here, that was 4 full wavelengths difference. And M equals 4. So you will get constructive interference anytime the difference in path from here to here, there, and from here to there was exactly 1 multiple of a wavelength difference. So 1 wavelength, 2 wavelengths, 3 wavelengths, and so on. So just in general, if this little segment here is a multiple of the wavelength, those are going to meet up crest on crest, trough on trough. You'll get a bright light or a loud sound or a tall wave in the water. Now we can take measurements of this. Let's measure the distance from the slits to the screen and call that L. And then we'll measure the distance from that first bright spot, we call that the central maximum, to one of the bright spots over here. So distance is x, but this is x sub m. This would be the distance to the first one, the distance to the second one, the distance to the third one. M is a multiple, it's an integer. And I could use tangent because the tangent of this angle equals opposite over adjacent. And then I could use, to solve, I could find the angle by using the inverse tangent of opposite over adjacent. And we can find this angle here. If I take this orange triangle and just flip it vertically, that orange triangle is similar to this red triangle. And if I take that orange triangle and shrink it down and rotate it and bring it to the side here, it will still be similar to that red triangle. And if this is a right angle here, this angle and this angle are going to be the same. The distance along the hypotenuse is the distance between the 2 slits. So there's a relationship between these 3 things. If I take the hypotenuse and I multiply by the sine of the angle, it will equal this opposite side. So d sine of theta equals a multiple of the wavelength. Now I said this triangle here was similar to this one, and that's not entirely true. They're kind of similar, but you can see that the outline here in the dotted black and the outline in the dotted white are slightly different. So this is an approximation. It's a pretty good approximation because the length of this is pretty close to the length of that, which was a multiple of the wavelength. But it is still just an approximation. In this case, it was a reasonably good approximation. If we come back to this example, where these are really far apart and it's off at a big angle there, this triangle here is very different than that right triangle there. So it'd be a pretty lousy approximation. But let's look and see when it would be a really good approximation. So here is our two slits and our screen. If those two slits are really close together, D is very, very small, and the length of the path between them is very large. In fact, we say that the length of the path is greater than the distance between the slits. 2 greater than means that that length of the path is much greater than the distance between these two slits. So if this is really small and this is really big, the ray that comes out here and hits a spot and the ray that comes out there and hits a spot, if those are different by a multiple of the wavelength, then this is going to be a pretty good approximation because those two lines are pretty close to parallel. So let's move that down. If they're parallel, then we can see that this red triangle here and this triangle here are both right triangles. This angle is going to equal that angle, and if these two lines here are parallel or nearly parallel, then we can go ahead and say that this distance, the hypotenuse times the sine of the angle, is a multiple of the wavelength. And we could measure the distance from the slits to the screen and measure the distance out to there and find the angle, and then we can plug in the angle into the equation. If we know the distance between the slits, we can find the wavelength. If we know the wavelength, we can find the distance between the slits. And there's one other approximation we can make, is that for small angles, sine and tangent are very close to the same value. So this blue line down here at minus 90 degrees, this would be at a minimum, and positive 90 degrees, this would be up at a maximum. And tangent curves around like this. But let's zoom in between minus 40 and 40, and we can see that in through here they're pretty good. Let's again zoom in from minus 20 to positive 20, and you can see, wow, for small angles, like maybe from minus 15 to positive 15, the tangent of an angle and the sine of the angle are virtually the same. So if they're really close to the same, and we have d sine of theta is a multiple of the wavelength, then we can just substitute tangent in for sine. Only works for pretty small angles. And since the tangent is the same thing as opposite over adjacent, well, we can substitute that in for tangent. And we don't even have to use a trig function. But we could solve that equation for lambda, or we can solve it for d, or we can solve it for the distance out to one of the spots. Now let's see how good of approximation this is. I just found the percent error of difference between the sine and the tangent of the angle, and found at 20 degrees they're off by about 6%. Okay? At about 8 degrees they're only different by 1%. And a little more than 18 degrees they're off by about 5%. In labs we try to keep our percent error of difference under 5%. So this would be a good equation to use if the angle out to those bright spots was less than 18 degrees. If we want to do even better, try to keep it less than 8 degrees, and you'll only get 1% error. All right, now instead of having just 2 little slits, let's have a bunch of slits. So tiny, tiny, tiny little slits here. Light is going to diffract through each little slit, but a pattern is going to emerge. And I'm saying that these lines here are all nearly parallel, so they meet up here, and all of these are nearly parallel and they meet up here. But you're going to get, if you shine a laser beam through a diffraction grating, you're going to get a very bright spot here, you'll get a bright spot there but not as bright, and you'll get a bright spot there but again not as bright. You'll get this will be the central maximum. This is when m equals 1, m equals 2, and the pattern's going to repeat. So let's see if we can understand why that happens. And just to see it before we do it, this is what a diffraction grating looks like. It just looks like a clear piece of plastic, but there's tiny, tiny grooves. In this case, there's 530 grooves per millimeter. If I shine green light through there, let me back up. If I shine green light through there, it's going to spread out at a big angle. Violet is a shorter wavelength, and it's going to spread out at a less of an angle. I'll explain why. So here's our diffraction gradient with tiny, tiny little grooves here. And all of these lines are nearly parallel. And this is the distance between any two openings. These are going to meet up at some angle. We could use tangent to find that angle. But if this path here is one wavelength farther than that wave there, then these two waves, those two rays, would line up constructively and it'll make a bright spot. But if this one is one full wavelength more than that one, then those two waves are going to meet up at a bright spot. This was one wavelength further than that one, but this was two full wavelengths further than that one, so all three are going to meet up at a bright spot. Okay, or all four would meet up, 5, 6. All of them are all going to meet up at a bright spot at some angle if each ray travels exactly one wavelength farther than the other. So again, this is the hypotenuse, and if you take the hypotenuse and multiply by the sine of that angle, it's going to be a multiple of the wavelength. And if we go out at even a greater angle, they'll meet up again constructively, but this time the difference in the path was 2 full wavelengths. So if this is 2 full wavelengths ahead of this one, those two meet up in a bright spot. If this is 2 full wavelengths ahead of this one and 4 full wavelengths ahead of that one, all 3 of them meet up in a bright spot, and the pattern continues where all of those are going to just be 2 extra wavelengths behind. And the distance between the two slits and the angle that they meet out there at a bright spot is going to be a multiple of the wavelength. Either 1 multiple, 2 multiples, 3 multiples, and so on. So we can see here that if we had a smaller wavelength, we should have a smaller angle. And that's where we had with the violet light. Now we need to find D here. It said this was 530 grooves per millimeter. Well, we can just take the reciprocal of that and we would get millimeters per groove. We usually like to keep things in MKS notation. So we're going to say 1 meter is the same thing as 1,000 millimeters. And then if I just take that, divide by this and that, this would be the distance between any two grooves, the D in our equation. So not quite 2 micrometers. And a diffraction gradient is often used to spread light out so that you can see what colors and what wavelengths are in light. This is hydrogen gas, and it looks like just one color, but the diffraction gradient spreads those out and creates these bands where we can see exactly what colors are there. The only thing that's different in this example is I'm looking off to the side and seeing a virtual image of where those bands virtually come together. All right, that was double slit interference and multiple slit interference, called a diffraction gradient. But now let's look at single slit. If there is a tiny, tiny little opening here, you shine a laser beam through it, it's going to spread that light out, it's going to diffract. But this time we see dark spots within that spreading out. So we have to try to understand where we get those dark spots from. So this time there's only a single opening, so we're not using D to find the distance between two openings. We're using A for the aperture. Aperture is the size of the opening. And there's going to be some angle off to the side here where you get a dark spot. And the way we find that is if we measure what the aperture is and find out what half of the aperture is. If half the aperture is the hypotenuse here, and this side here is half of a wavelength, this ray here is going to arrive half of a wavelength behind that one, and half wavelength behind, they'll be out of phase and destructively interfere. But these two would cancel, and those two would cancel, and those two would cancel. You're going to find a ray in the lower half canceling with its counterpart in the upper half, and everything's going to cancel out. So here's the hypotenuse of that triangle, half the aperture, and this side here is half the wavelength. The hypotenuse times the sine of the angle equals that opposite side. And if I multiply both sides by 2, we get this equation, which is very similar to our previous. We find that m equals 1 is going to predict where the first dark spot is. But there's another angle that we can find another dark spot, and it's going to be a much larger angle, but this time half the aperture was 1.5 wavelengths, or 3/2 of wavelength. If this ray here went 1.5 wavelengths farther than that ray there, then those two rays are going to cancel out, and these two rays will cancel, and those two rays will cancel, and those two will cancel. Every one in the lower will cancel out with one in the upper, but half of the hypotenuse was 1.5 wavelengths. So hypotenuse times the sine of the angle is 3/2. Multiply both sides by 2. I get that equation, and we see that when m is equal to 3, it also cancels out. And you can imagine that 5/2 and 7/2 and so on, all of the odd multiples are going to create dark spots. But that's not it. That's not all. There's an angle between those two that would also create cancellation and dark spots. And this time, if we have a quarter of the aperture for the hypotenuse and the opposite side was half of a wavelength, so this is still a half wavelength like this one was, these two would cancel out, those two would cancel out, skip on ahead and those would cancel, that would cancel, and again, everything's going to cancel, and you're going to get no net light. It will be a dark spot. If I multiply both sides by 4 to get rid of this fraction, I'm going to get that a multiple of 2 also works. So right there, a multiple of 2 also works. So you can see this, that, and that just had ever increasing multiples of the wavelength. We'll get dark spots. And with single slit diffraction, this time it predicts dark spots, but you're going to get one bright spot, and you're going to get these equally spaced dark spots. And because these are such small angles off to the side, we can use that substitution with sine and tangent and see that if the wavelength is constant and the length is constant and the distance between them is constant, if this is 1, it's going to be some distance. If it's 2, it's going to be twice that distance. 3 is going to be 3 times that distance. They'll be at equal distances. All right, that was single slit diffraction. So if I put a single slit there, it's going to spread out and we're going to have these dark spots. But instead of having a single opening, let's have a single closure, like a really tiny little thin tube here, like a human hair. If you put a human hair here and shine a laser beam here, you're going to get the same pattern as when it was open versus closed, for the same reasons. So here's a human hair. I'm shining the laser beam in here. It spreads out, and we can't see real well, but the aperture, or the opening, or this time the closure, the diameter of that, is going to be a multiple of the wavelength. I am going to go ahead and substitute sine and tangent for each other because the angle out to the center and the angle out to there are such a small angle. It's a pretty good substitution. And then I can solve for the aperture, or the diameter of that hair. So let me zoom in on that again and put some numbers here. So it was 140 centimeters from the hair out to the wall, and the first dark spot was 0.7 centimeters away, 1.4, 2.1, and 2.8. I can look at the laser and read right off the laser that it was 532 nanometers. So we know the wavelength of the light, 532 nanometers, and I can find the diameter of that hair at 0.11 millimeters. Very small. I could have done that with m equals 2, is twice the distance, and we get the same answer. M equals 3 was 3 times the distance, and m equals 4 was 4 times the distance, but we should get the same number all the way across. Now, instead of having a single opening here, if we just rotated this horizontal, that would rotate vertical. And instead of having just a single slit here, let's put another horizontal slit there. You're going to get a pattern horizontal and one vertical. But instead of having this, let's put a hole there. It was a square here, getting these two patterns. But if I had a circle there, like a tiny, tiny little pinhole, it's going to be the same pattern all the way around. And you can measure the diameter of that hole by measuring out to the dark spots here. Okay, and instead of having a single hole, let's have a single dot, like a red blood cell. If this was a single red blood cell right there, you can measure the diameter of that red blood cell by measuring that pattern. And that's what I promised we would do at the beginning. So we're shining the laser beam through here. It diffracts all around, makes this pattern. This was the distance out to the wall, our screen. This was the distance out to the first dark spot, and the second dark spot, and the third dark spot, all the way out to here. But we can use tangent to find the angle, and we know the wavelength, and now we know the angle. We can find the diameter of your blood cell. It's 6.7 micrometers. We could do that for when m equals 2. Okay, out to here, it's going to be a bigger angle. And these angles are big enough that I'm not using this approximation for sine and tangent. I'm actually using tangent to find the angle. So it was twice the distance, but it's twice the multiple of the wavelength. There, we get the same answer. And then, see, that's a pretty large angle there. But we do get the same value all the way through. And normal red blood cells are somewhere between 6 and 8 micrometers. And we were doing pretty good there. So just to pull this all together, double slit, d sine of theta is a multiple of the wavelength. 0 is going to be our central maximum, and then 1 wavelength, 2 wavelengths, 3 wavelengths difference. But this predicts bright spots. If it is a single slit or a tiny little pinhole or a red blood cell, it's going to be the opening or the size of that hole, and it's going to predict dark spots. We do have to use tangent to find the angle if we're pretty large angles. It would get us pretty big percentages of error. If we don't have big angles, then we can just substitute sine in for tangent and come up with that equation there. A lot to keep track of, but I think you guys are doing well, and you might need to watch it again just to make sure.